Welcome to Mr. Alvarez's virtual chemistry classroom. Today we'll be learning about significant digits, which is also the same as significant figures. Our aim for today is how can we determine which numbers in a value are significant. But first, let's talk about measurement and uncertainty. Now, every measurement has some level of uncertainty. That level of uncertainty is all dependent upon the device that is being used to make that measurement and the user's ability to use that device to make that measurement. Now, in this diagram here, we have a graduated cylinder filled with some amount of water. We can see in the zoomed in pictures that we have a little bit more than 21 milliliters of water, but a little bit less than 22 milliliters of water. I'm going to enhance the image. You can see a little bit better. So we have a little bit more than 21 and a little bit less than 22. We also could see in this very zoomed in image that the meniscus, the bottom of the meniscus, is a little bit higher than halfway between the 21 and the 22 milliliter marks. So we can estimate that there is 21.6 milliliters of water in this graduated cylinder. We know for a fact that there's a little bit more than 21 milliliters, and there's less than 22. So it's 21 point something. This digit here, this 0.6, we estimated because the meniscus, once again, is a little bit higher than halfway in between the 21 and the 22. And that brings us to significant figures, or significant digits, which are the same thing. Significant figures are all of the digits in a measurement, including that last uncertain digit. Now, any non-zero number is always going to be significant. So if you have a measurement and you see either a 1, a 2, a 3, a 4, a 5, 6, 7, 8, or 9, those numbers will always be significant. Where we run into a little bit of trouble is when we have a 0 in a measurement. Now, we're going to go over the rules now of when a 0 is significant and when a 0 is not significant in a measurement. Rule number 1 has to do with non-zero digits. Now, rule number 1 states non-zero digits in a measurement are always going to be significant. So, for example, 7.2, I have two numbers. They're both not zero. So this value has two significant figures. 824, 824 are three non-zero digits. So this value has three significant figures. 927.22, 1, 2, 3, 4, 5, this number has five non-zero numbers. So this value has five significant figures. And finally, 3.333, there are four numbers that are not zero. Therefore, this value has four significant figures. I like to call rule number 2 the sandwich rule. Now, rule number 2 states zeros between two significant digits in a measurement are significant. Remember, any non-zero number, 1, 2, 3, 4, 5, 6, 7, 8, or 9, are always going to be significant. It's when we have a 0 in a measurement, that's where we run into some trouble on whether it's significant or not. So, for example, for the sandwich rule, for letter A, we have 1.609. Any non-zero number is going to be significant. Therefore, the 1, the 6, and the 9 are going to be significant. Now we have to look at the 0. According to the sandwich rule, a 0 between two significant non-zero numbers is also going to be significant. This 0 is sandwiched between the 6 and the 9. So in this case, all four numbers in this measurement are significant. For letter B, 302. The 3 is not a 0, and the 2 is not a 0. So those are definitely going to be significant. We look at the 0, and since the 0 is sandwiched between the 3 and the 2, that 0 is also significant. significant. So in this case, 302 has 3 significant figures. Letter C is a little bit trickier. We have a decimal point involved, but we have an 8 here, and we have an 8 here at the end. So we have the pieces of bread in a sandwich, and then we have the zeros in the middle. There are 2 zeros sandwiched between those 2 8s. So in this case, once again, all of the numbers in this measurement are significant. So we have 1, 2, 3, 4 significant figures. And finally, 40.003, we have the 4 in the beginning, the 3 at the end, and in the middle we have some zeros. They're going to be significant because we have the 4, a non-zero number, and the 3, another non-zero number, at the ends. So in this case, I have 1, 2, 3, 4, 5 significant figures. Rule number 3 tells us what to do with trailing zeros. Now for rule number 3, all final zeros to the right of a decimal point after a non-zero number in a measurement are significant. So for example, letter A, I have 4.0. The 4 is a non-zero number, and then I have a decimal point, and to the right of that decimal point I have a 0. That 0 will be significant because it's after the decimal point, to the right of the decimal point, after a non-zero number. So in this case, for 4.0, both of those numbers are significant, so 4.0 has 2 significant figures. For letter B, 74.00, very similar. I have the 7 and the 4, both non-zero numbers, so far I have 2 significant figures. Then I have a decimal point, and then I have 2 zeros. Since those zeros are to the right of the decimal point, after a non-zero number, both of those zeros are significant figures. So for letter B, 74.00 has 4 significant figures. Letter C, we have 612.600. Once again, 6126, they're all non-zero numbers, so they're all significant. Then we have some zeros. Even though the 6 is here, that's okay. We still have a decimal point. We still have significant figures, non-zero numbers, so that means these zeros to the right of the decimal point are also significant. So we count them up, 612.600, 1, 2, 3, 4, 5, 6. This measurement has 6 significant figures. And finally, letter D, 21.330, we find all the non-zero numbers, 1, 2, 3, 4. So the 2, the 1, the 3, the 3 are all non-zero. We have the decimal point right here. And the 0 is to the right of the decimal point after a non-zero number. So this 0 is also significant. Count them up, 1, 2, 3, 4, 5. 5 significant figures. Rule number 4 shows us how we should handle leading zeros. Now, rule number 4 states, in a measurement, zeros that exist only to put the decimal point in the correct place are not considered significant. So, for example, 0.2, that 0 is just a placeholder 0. It has to be there to put the decimal point in the correct place. It does not tell us anything about the measurement. So in this case, we forget about that first 0, and that 2 is going to be the only significant figure. You have to start with the first non-zero number. Same thing here, 0.0025. Those zeros are just placeholder zeros. They're only there so the 2 and the 5 can be in the correct spot. So the 2 and the 5 are non-zero numbers. They are significant. So this number, 0.0025, has only 2 significant figures. For letter C, very similar. 0.0, they're just there to make sure the 7, the 6, and the 4 are in the correct decimal location. So we have the 7 in the 100th spot, the 6 in the thousandth spot, and the 4 in the 10,000th spot. So those two zeros are only there to make sure the 7 and the 6 and the 4 are in the right locations. Therefore, 7, 6, and 4 are significant. The two zeros are not, so our value here for letter C has 3 significant figures. And finally, letter D, 0.00000093. Once again, these zeros are only there to hold the place, to make sure the 9 and the 3 are in the correct location. If they weren't there, this is a completely different number. 0.000093 is a completely different number than 93. Those zeros, once again, are only there to hold the place. And these two non-zero numbers, 93, 9, and 3, are the only significant figures in this measurement. Rule number 5 tells us what to do with final zeros if there is no decimal point. Rule number 5 states, if there is no decimal point, final zeros in a measurement are not significant. So for example, 10, no decimal point. This 1 is the only significant figure. Very similar to the last rule, this 0 here is only there to hold a place, to make sure that 1 is in the proper location. 10 is a very different number than 1 if the 0 was gone. So it's just a placeholder 0. So for 10, only the 1 is a significant figure. Same thing for letter B, 310. The 3 and the 1 are significant, but this 0, once again, is just there to hold a place. Therefore, 310 only has 2 significant figures. And it works with bigger numbers as well. 78,000. The 7 and the 8 are non-zero numbers, so they'll always be significant. But these 3 zeros here at the end are just placeholders. So the only 2 significant figures in this number are the 7 and the 8. And finally, 234 million. The 2, the 3, and the 4 are non-zero numbers, so they are significant. But these zeros are just placeholder zeros. So these zeros are not significant. Therefore, 234 million will have 3 significant figures. And finally, rule number 6 tells us what to do if we have a decimal point at the end of a measurement. So rule number 6 states, if there is a decimal point at the end of a measurement, all the numbers to the left of that decimal point are significant. So for example, A, remember before when we had 10 with no decimal point, that was just one significant figure. But now, if we put 10 with a decimal point, that scientist or whoever is writing down that number is telling you that they measured to the nearest whole number here. So therefore, 10 with a decimal point at the end will have 2 significant figures. Similarly, letter B, remember, no decimal point, 310, 2 significant figures. But you put that decimal point at the end, 310 with a decimal point, someone is telling you they measured to the nearest whole number. So in this case, 310 decimal point will have 3 significant figures. That last 0 is going to be significant. 78,000, before without the decimal point, just the 7 and the 8 were significant. But you put that decimal point at the end, that makes all the zeros to the left significant, as long as we have a non-zero number. Therefore, 1, 2, 3, 4, 5 significant figures. And finally, 234 million with a decimal point at the end. Remember, no decimal point, 1, 2, 3 significant figures. But if we have exactly 234 million of something, you put the decimal point at the end, and that makes all of the zeros significant. So 234 million with the decimal point at the end has 9 significant figures. Let's go through these problems together. For problem number 1, 1, 4, 5, and 4 are all non-zero numbers. So rule number 1 states all non-zero numbers will be significant figures. 1, 2, 3, 4. Question 1 has 4 significant figures. For question 2, looks like rule number 2, sandwich rule. We have the 2, the 5, and the 2, and in between the 5 and the 2, we have the 0 sandwiched in between. So once again, 1, 2, 3, 4, we have 4 significant figures because the 0 is going to be significant, sandwiched in between the 5 and the 2. For rule number 3, that is going to be, we have 8, 7, and then we have a bunch of zeros with no decimal point. That is rule number 5. Trailing zeros, no decimal point. These 3 zeros only exist to hold the 8 and the 7 in its proper location. So 87,000 is going to have 2 significant figures. 3 and 4, questions 3 and 4, are different from each other. Here we have 87,000 once again, but now we have a decimal point at the end. Rule number 6 states we have a decimal point at the end of a number, then the zeros to the left, as long as we have non-zero numbers, will be significant. Someone put that decimal point there, some scientist or someone measuring something, put that decimal point there to let the reader know that they measured exactly 87,000 of something. So all of these zeros, they're not just placeholders, they are significant as well. So that decimal point means that the 8, the 7, as well as the 3 zeros are all significant. So this answer will have 5 significant figures. For question number 5, we have 0.00211. Now we know the 2, the 1, and the 1 are going to be significant because they are non-zero. But here we are dealing with rule number 4, leading zeros. These zeros only exist to hold the place for the 2, the 1, and the 1. If those zeros were not there, those 3 numbers would not be in the right decimal place. So they're just placeholder zeros. They're not significant. They do not tell me anything about a measurement. So for this question, question number 5, 0.00211, only the 2, the 1, and the 1 are significant. So this question has 3 significant figures. For number 6, we have 3,210. 3, 2, and 1 are all significant because they are non-zero. But here we have a trailing 0, no decimal point. So this 0 is just there to hold the place of the 3, the 2, and the 1, to make this number 3,210. So only the 3, the 2, and the 1 are significant. Therefore, this question has 3 significant figures. Number 7, we have a 6, and we have a 1 in 60,001. These zeros are sandwiched in between the 6 and the 1. Therefore, according to rule number 2, which I call the sandwich rule, these 3 zeros are significant. So count them up, 1, 2, 3, 4, 5. 60,001 has 5 significant figures. Nice easy one for number 8, 654. All 3 numbers are not 0, so 654 has 3 significant figures. Question number 9, the 4 and the 2 are definitely significant because they are not 0. However, once again, these leading zeros are just there to hold the place. They are not significant. They do not tell us anything about the measurement. They're only there to make sure the 4 and the 2 are in the correct decimal position. So question 9 only has 2 significant figures, the 4 and the 2. And finally, for question 10, we have 22.00. Of course, these 2 2's are non-zero numbers, so they are both significant. Then we have this decimal point and 2 zeros. Now this is rule number 3, trailing zeros after a decimal point. Since we have significant figures, non-zero numbers, before the decimal point, and zeros after the decimal point, these 2 zeros will be significant according to rule number 3. So if we count them all up, 22.00, all of these numbers are significant, so question 10 has 4 significant figures. Thank you for joining Mr. Alvarez's virtual chemistry classroom. Today we learned about significant figures, which are also known as significant digits. We learned about uncertainty in a measurement, And we also learned how to determine the number of significant figures in a given measurement. Thank you again for joining us. I hope you learned something today. Please join us again soon.